Thank you very much, George. Let me introduce myself. I am Evangelos Mathas from CRES, and I will present you the use of these products that you've seen so far in the previous presentations in real operating conditions. As you've already heard, we have three demonstration sites, one in Derio, Spain, one in Greece, and one in Belgium. We have two products here, the façade and the Skylights in Spain. We have three types of products in Greece, the flat façade, the window shadows here and here, and the balconies here. This is the side view, this is the front view of the two semicircular balconies. And in Belgium, in Mons, we have a beautiful south-facing roof, this part of the roof, which has been where real BIPV modules have been installed with a very with an excellent aesthetical effect. Starting from the Spanish side, this is the name of the building. It is in Zamundio, and it is composed of two buildings. One is for testing laboratories and the other one is for offices. The later one is the one with the ventilated façade and skylight products. So there are two PV installations there. The southeast façade has been covered with an innovative ventilated façade. This solution combines an aluminium standard construction system, which is a bit different than the one that we have used in Greece. And the concept is based on the direct integration of composite module over an aluminium component by Astrowall. The installation includes 34 modules, a total power of 2.5 kilowatts, and for 20 square meters. Estimated energy production is 2,100 kilowatt hours per year. You can understand that these modules, well, almost all of them for all sites, have been installed from the mid of last year, so we haven't got for any of the sites annual data for the real annual production. Estimations have been done for all of them using the PVGIS system software. And let's go to see some more pictures. Here you see where the installation takes place here, and you can see a man standing here just to give you a sense of size. This is the module, this is its drawings, flat and side drawings, and this is the back of the module. These are some few pictures from the construction operations. This is the skylight on top of the building. You've already seen this sketch of how it is designed, and this is the view of the skylight. Here is the view of the skylight from the inside of the building looking towards the top, the roof. Okay. Here is the design again. These are pictures showing the installation of the products. They are quite good looking skylight designs produced by Athens. And this is the electrical scheme. It is two single phase PV systems, one for the façade, one for the skylight, and they are operated under self-consumption, which means there is no injection of energy into the grid. Having this in mind, it means that there is no point of installing more power than necessary, and we will have a look at that later at the diagram. What does that mean? So, as it says here, with zero grid injection, there is no economical sense for as long as the Spanish legal framework for photovoltaics is concerned. There is a monitoring system, and the monitoring system is important to know that exists in all three systems. All demo sites are monitored for a long period of time, at least 6 months before the installation of the PV systems, just to get an idea of the consumption profile of each demo site, of each building. And then monitoring continues with the PV systems installed in order to see peaks, balance of energy and power, etc. Here we see an interesting diagram of what I just said earlier. Here you see that the production is just under the consumption, the daily consumption of the building. Here you see the two systems, the façade and the skylights, and this is the total of the three, which is represented also here, together with building consumption. And here we see the same case, that is again the two systems shown here, façade and skylights. It's some, there are some up here, but here you see that the system produces more energy, power than what is consumed. So what we said earlier about the Spanish legal frame, this energy right here is lost. Let's come now to the Greek demo site. The building is a low energy consumption residence, completely designed and built by Heron, and it's equipped with a geothermal heat pump which covers the heat, cooling and hot water needs by 100%. It's an interesting case, this building, this house, because it is 100% an electricity consumption. There is no other part of energy taking part in its use. It's fully electric with CRES, with a geothermal pump. So it's quite important to have, and interesting to have a PV system installed there under the net metering law that it has been existing in Greece for the past year or so. And we will see now, and knowing also that its mean annual consumption is about 3 to 3.5 megawatt hours per year. We will see the systems installed, is the shadings here, the shadings here and here, using just a cantilever system to hold them in place, and they're holding place also there. The façade system and the balcony system. It's important to note, and you will see that I think in the next slide, this one, it's important to note that these panels here, the façade panels and the two shading panels, are at right angles to the balcony panels. So here are the façade, here are the shadings, and here are the balconies at the 90 degrees to the other. You realize that such a system could not be connected to a single inverter. You will have great problems in showing production. So the solution of microinverters was chosen, as mentioned earlier by Jose, so that not only each system produces its maximum available, but also it doesn't affect the others, not only between systems, but even within particular panels. And in this way, we have the ability to monitor each particular module by itself. That is very important for, let's say, monitoring and scientific purposes. Monitoring again is present, as I said earlier, in all three sites. This is the design of the monitoring system designed by CRES. It is based on a series of controllers which are termed smart structure, and they are made by Schneider Electric. They are network automation servers with TCP/IP and support IPv6 technology, being a full modular model that you can add up as many more sensors as you like. Here we see the monitoring screen developed by CRES. This is the electrical consumption data of the building, that is consumption data. This is the internal, this is the meteo data and internal comfort conditions. Internal comfort conditions are important for one reason that I will explain now. Here you see the temperature in two lines. These are two thermometers which are placed inside the house on the wall that has the façade. One of them is on the wall that has the façade in front of it, and the other one is on the side wall that hasn't got the façade on it. So by using these two thermometers, we're trying to establish if the façade, that is the PV temperature that goes up, as we know, during operation, it can go up to 60 degrees and even more, if the actual façade gives any effect to the internal side of the wall of the house. Up to now, if you see here in the numbers shown, the difference in temperature is about half degree at maximum. This, of course, is the external environmental temperature of the site. And here's the irradiance per day of the systems. And I mean monitored by a pyranometer. Here we see the PVs. You see on the menu we have clocked PVs, and you see the voltage close to 2230. You see the power active. This is actually today's picture. We've just downloaded that to show you real-time data, even though in a frozen picture. You see that at around 11 o'clock, the three systems, because the microinverters are packed together in three SMA multigates, are producing normally. And the electrical connections are done in that way to the microinverter location of grid faces and to the AC distribution board of the local grid operator. And this is also today's picture of from the Sunny portal of the SMA microinverters. You can see the system here, that is the façade, and this is a representation of the balconies. And if you just select one of the panels, you see all its characteristics. For example, it is made by Acciona, it is placed at -45 degrees orientation at an angle of 90 degrees, that is vertical, its serial number, its power, and on the Sunny multigate, that is the system from which we get the info from. This is important because if you check the numbers shown here, you will see, as mentioned earlier, that actually a couple of modules are producing less, a couple of façade modules, for the simple reason explained earlier by Jose, that the two window shading systems throw shadow on them, depending, of course, on the time of the day. It is also important to see here that we have the three Atersa façades, which use the same cells as the ones used in the other products, and their production is shown, and this is an excellent way of compare the two technologies, that is the one we developed and the one which is, let's say, normal to our products. This is the finished house. You can see the balconies and everything, and here you can see in front of the house, you can see the meteo mast that we get the environmental data from. We're going to Belgium now. This is the building cut roof. as you've seen before, and it looks very nice. The demo site in Belgium has a beautiful south-looking roof at a very nice inclination. So some pictures from the installation, the solution chosen for the rich tile clay in order to be above the last PV panel, the last PV shingle. And another picture, this is a particular beautiful picture of this demo site. It's not only a real but a very beautiful application of BIPV systems. Electrical setup is shown here inside the house at the top plan. These are the two SMA microinverters here under the roof, and here is the screen that the inverter brings out to the user. Monitoring, again, it's very important, is here again present. Optimal computing designed a very nice web data access and a very nice monitoring system. Of course, all communication and monitoring of all three systems is on the internet. And of course, he used also monitoring the outdoor measure details and the indoor by placing some thermometers under the roof, here and here and here, in order to check that the roof underneath is not, let's say, heated up by the heat that is getting out of the modules, in a similar way that we did for the demo site in Greece. Here we see the thermometer placed on the roof before we placed on top on this structure the panel. And this is the website that gets out to the user monitoring. You can select every interesting parameter from this list, check the dates and the times you went, and you can download data. You can see here insolation, and you can see power. And thank you very much for your attention. And now, if there is no question, we can go next to the next presentation.
Thank you, Evangelos, for your talk. And now to